Section 3.4, we're going to continue down this trail of talking about what derivatives do for us in terms of graphs. In 3.4, we're going to talk about something called concavity. Who has heard the word concavity before? Just raise your hand. Okay, about half of you. Concavity is sometimes discussed when you talk about curves in geometry. You heard the words concave and convex. That's concavity. Okay, so that's where sometimes we'll hear it discussed. Sometimes also discussed in like an Algebra 2 class, high school, when you talk about parabolas the first time. And it talks about a graph being concave up. It looks like it holds water. And then sometimes it's talking about the graph being concave down with a parabola where it looks like it dumps the water out. So you may have heard it in those contexts. We're going to be using it more from that second context than from the geometry context, although they are related. We're going to define concavity a little differently, though, because we're not specifically looking at parabolas, so this idea of holding water probably isn't going to fit very well. Concavity says the following. For a function f that is differentiable on the interval I, the graph of f is concave up if f prime is increasing on I, and it's concave down on I if f prime is decreasing on I. And I is just some interval, so some portion of the graph. Concave up on a portion of the graph when the derivative is increasing, and it's concave down when the derivative is decreasing. I think a picture might be helpful to justify why this is describing. So what does it look like for the derivative to be increasing? So what does the derivative tell us about a graph? Slope. It tells us about slopes. So if the derivative is increasing, it means the slope is increasing, right? So a slope increasing means it's getting steeper over time. So if you think about drawing tangent lines here, the tangent lines get steeper as we go, right? This is what we would consider something that was concave up. All right? The steeper the slopes get as you move through whatever the interval is from left to right. We consider something to be concave down when the slopes are decreasing. So if you take a look at something like this, these slopes, when I draw tangent lines, are becoming less steep as we move from left to right, aren't they? So when the slopes are leveling out, that is considered something that is concave down. That still fits in with the idea of parabolas that we learned back in maybe like an algebra course somewhere. It still works with that. But this is defining it from a little bit different perspective because we have derivatives to be able to talk about now. All right, so let me talk then about how we talk about concavity when we consider the original graph of something and the second derivative instead of the first derivative. Suppose that f double prime exists. We've talked about f double prime before, right? Just means the second derivative. When the second derivative is positive, we would say that the graph is concave up. And when the second derivative is negative, then the graph is concave down. Okay, so I want to make some connections for you that this theorem, I'm not going to prove this theorem, but I am going to justify it based on what you already know from the last chapter, or last section of this chapter. So jot those details in, and then I'm going to go back to the previous slide. Okay, so this is talking about f being concave up. On the last slide, it says that it's concave up if f prime is increasing. So this is when f prime is increasing. All right, so think what happens when we have an increasing graph. So ignore primes and all that kind of stuff. Just think for a moment what happens. When you have an increasing graph, what happens when you take a derivative on the portion of the graph where it's increasing? What do derivatives tell you? Slopes. So if the graph is increasing and you take the derivative, then the slope is going to be positive, right? An increasing graph means a slope is positive. So the derivative, what is the derivative of f prime? F double prime. So if the derivative is increasing, then the derivative of the derivative would be positive. Because a graph that is increasing has a positive derivative. So do you see the connection? That's all this theorem is doing, is it's making the connection from the outsides of this diagram. we're saying if we have an original graph that's called concave up, then by definition what we mean is that the derivative is increasing. But when the derivative is increasing, or when any graph is increasing, and we take its derivative, we get a positive slope value. And that positive slope value just happens to be the second derivative of what we began with. We're just going down the bunny trail as we go. And the second part of this theorem with concave down works the same way. So if I have a graph that is concave down, then according to the definition on the previous slide, that means that the derivative is decreasing. Well, when we take the derivative of something, in this case, the name of that would be the second derivative, then if a graph is decreasing, then its derivative is negative. So again, the outsides of this tell you that if the second derivative is negative, that in and of itself is the same thing as saying that the original graph is concave down. All right, so let's take a look at how this information plays out when we're working some problems. Oh, I'm sorry, I have one more definition. I'm sorry, I missed right over it. Inflection point. This is an important piece of information. Again, you might also have heard this word before, but probably less likely than concavity, although when you talk about concavity, this often comes up. An inflection point is simply a place where concavity changes. The graph is changing from being concave up to being concave down, or vice versa. So let me draw you a couple of pictures of how this might look on a graph. This is just that plain old exaggerated looking, but plain old graph of y = x cubed. If we were drawing slope lines in here, you know, those tangent lines, for a while they are actually becoming flatter, right? I can't get that last one drawn quite right. But as you move from left to right, for a while the slope lines get flatter as I move towards the middle of this graph. But after I move away from the middle of this graph, somewhere around right here, and I try to draw those slope lines, they get steeper again. Right? So this point that's in the middle, this blue point, is called an inflection point. The graph to the left of it is what's considered concave down. It's got this downward sort of curvature. And the graph on the right of it is considered concave up. It has this upward curvature. And the place where it changes concavity is called the inflection point. And sometimes you actually have something where it's a little bit more dramatic. So this is another x cubed kind of curve, but it would have more terms in it than just y = x cubed. This one would be something like this particular point right here, roughly speaking. To the left of this, you have the curvature where it's opening downward, and to the right of it, you have the curvature where it's opening upward. So that particular point as well, it's changing concavity. Okay? So think with me for a second here, because we're about to hit, let me see where it is. We'll hit it in a second. But think what happens when we're changing concavity. We just said on this previous slide that if it's concave down, what can you tell me about the second derivative? It's negative. Very good. And over here, it's concave up. What can you tell me about the second derivative? It's positive. So what in the world do you think happens at a point of inflection? Changes. What would it equal? 0. It's supposed to be negative, and then it's supposed to be positive. So at that place where it's changing from negative to positive, that has to be 0. It's basically a intermediate value theorem issue that we've experienced before. If you can't go from negative to positive and not pass through 0, this is the point where it's 0. Okay? We do have the possibility that does not exist as well. We could have something like an asymptote there. That would be a possibility. All right, so let's take a look at how this actually works in terms of a graph. This example says it wants us to determine the intervals where the graph of this function is concave up and concave down, and then determine or identify any inflection points. So if we're talking about concavity, This is one of those things that should just be ingrained in your mind when you hit that test in, I don't know, a week or wherever it is that concavity is talking about the second derivative. So if this question asks you about concavity, you know you're going to be finding second derivative. And second derivative is just the derivative of the derivative, which means you got to find the first derivative first. So what is the derivative of this wonderful polynomial function? Y'all are fantastic and awesome at doing derivatives now. So what's this one? Okay, did everybody get that? Good. And then we're going to do the derivative of that, so the second derivative. So what do we get for the second derivative here? Okay, is everybody good with that? Some of you were saying, why wasn't that the question on the quiz that she asked me, right? Yes. All right, so some pretty straightforward derivatives when we're looking at these. Okay, so what we want to know then, according to how we've described this over here, is we want to know the place where the concavity is positive, where the concavity is negative, and then inflection points, that means where the concavity is 0. How do you think we might do that? How do we find out where something is positive, negative, and 0? What's that? Set it equal to 0. This is exactly what we did in the last section. We weren't finding the same information, but it is found in the same way because we're using the second derivative to do it. So we set it equal to 0, and we factor. We solve. Okay, whatever the solving requires. In this case, it's factoring. You could do this one with factoring. You don't have to necessarily because there's not a linear term in the middle. You could actually put this to the other side and simplify from there, and that would be okay. So if we factor, we would factor out a 12. I'll show it another way in a second here, and I'd have x squared minus 1. How does x squared minus 1 factor? Yeah, so we've got x minus 1, x plus 1, and then x equals plus or minus 1. Another way you could do this from here, because it's not a trinomial, you could actually move the 12 to the other side, divide by 12, and take a square root. The only catch to doing that is to remember that when you take a square root, you need to put the plus or minus on there. Don't forget that. Okay, so either of those would work for this one. This gives me two values where the second derivative is 0. So what does that tell me about those two locations? I may have it changing, right? Maybe. They're at least, it's kind of like critical points. We don't call these critical points, but it has that same sort of feel to it. It's a location where the second derivative, I keep saying it wrong, the second derivative may be changing. So how do I find out if it really is changing? Okay, we're going to graph it. We're not even going to graph it the whole way. We're going to do a number line graph, though, for it. Okay, so we're going to set up a number line like we did in the increasing, decreasing section that we did. And on our number line, the only points that matter are what? 1 and negative 1. I shouldn't have said it that way. But those are the points where I'm going to draw on the graph. I don't need to draw any of the other ones on there. The points in between are actually the ones that matter for me. I need to pick a point in each of those locations. So somebody tell me a point that you would like to pick on the left-hand side of negative 1. All right, negative 2 it is. How about between negative 1 and 0? Or between negative 1 and 1? 0. There, I said it. And then after 1? 2. Now, what is it that I want to know is changing? Or I'm asking if it's changing. What is it we're looking for to see if it's changing or not changing? Not the slope. Not this time. The concavity, right? This question is about concavity. So I need to know what the concavity is doing. And where do we find information about the concavity? Which equation? The second derivative. So these particular points that I've picked, negative 2, 0, and 2, I'm going to plug them in, but I need to make sure I'm plugging them in the right place. Where should I be plugging them in? The second derivative, because that's the only piece of the graph that gives me information about concavity, at least from the perspective that we're working at this point, this particular point of the problem. So we're finding, well, we called them y before, y double prime of negative 2, y double prime of 0, and y double prime of 2. want to make sure we're plugging them into the second derivative equation. And that second derivative equation is the one that we wrote down right here. Not where we set it equal to 0. We did that to find those locations. But before we set it equal to 0, that was the second derivative. All right, so tell me what you find out. What happens when you plug in -2? And again, what I want to care about is the sign, right? Positive. What happens when you plug in 0? Negative. And what happens when you plug in 2? Positive. Okay, so what we had done before is we drew these sort of lines that went up and down, right? Positive means I go up, negative means I go down. That's not what this graph tells me, though, right? It tells me about concavity, correct? So what does a positive on this number line tell me? It's concave up. Exactly. Very good. So on this graph, this is telling me that it's concave up here and here. And what happens in between? It is concave down. So does the concavity actually change at -1? Yes. It changes from concave up to concave down. Does it actually change at 1? Yes, it changes from concave down to concave up. So the next question then is, do I in fact have inflection points at -1 and at +1? Yes, because the concavity really did in fact change. So let's answer the questions now that we are asked. We're asked several things. We're first asked where the graph is concave up and concave down, the intervals. There's the word I was looking for. Intervals. So where is the graph? Whoops. I'll do it right here. Where is the graph concave up? Intervals. -infinity to -1, union, 1 to infinity. Those are the intervals on the graph where I had those concave up features, and I can read them straight off the number line below. Where's the graph concave down? From -1 to 1. Good. And the last thing says identify inflection points. You'll see it abbreviated a lot of times as POI, point of inflection. You can write it out, it doesn't matter, but I'm going to abbreviate it because I'm running out of space. So these are my points of inflection. I have 2 of them, don't I? I have one at x equals -1 and I have one at x equals +1, but this says inflection points. What is that telling me? What's a point? An ordered pair. I need to find y, right? All I have right now is x. Don't group the -1 and the 1 together. That's not the ordered pair. I have 2 ordered pairs. I have one of them at x equals -1 and I have one of them at x equals +1. How am I going to find the corresponding y value? The original equation, this one right here. I need to plug in -1 to the x to the 4th minus 6x squared plus 2x plus 3. Did you get a 1?
No.
No.
I was asking, when we're writing the ordered pair for concavity where it's going up and down, don't we have to do a close bracket?
That's a good question. So they aren't ordered pairs, they're intervals, first of all. Yeah. So your question is, when you do the interval, how do I write it? The intervals for concavity are always written open-ended because they don't actually have concavity at any particular point. There's no particular point that we're looking at. And in particular, if we actually looked at these at -1 and 0, we actually have the concavity changing at those locations, don't we? So it's not actually concave up or concave down at those end points on this particular graph. Yeah, those are the places where it's changing. All right, what happened when we plugged in -1? Did you guys get a value? 0. Really? Wonderful. What? Oh. Now I got 2 answers. Which one is it? What do I have written down? Oh. You guys gave me the 2 answers for the 2 parts. Was it like this?
Yeah.
Okay, sorry. I was mishearing. All right, so I have when I plug in the number 1, I get 0. When I plug in the number -1, I get -4. Does that look okay? Okay, so this answered all the questions now, right? Got all our concavity intervals, and we have the location for the point of inflection. And there's 2 of them in this particular one. All right. second derivative test. This actually gives us a third way. We have encountered 3 different ways in 3 different sections of finding maximum and minimum values. One way of finding maximums and minimums involved us using those critical numbers and then looking at a graphing device, making decisions. The second way that we looked at is we found the first derivative, and then we used kind of a sign chart, and we looked at the derivative on either side. Is it increasing? Is it decreasing? Do I have maximums? Do I have minimums? This is our third way. This is called the second derivative test. So suppose it's the second derivative, f double prime of x, is continuous on the interval a to b. And f prime of c is equal to 0 for some number c in the interval. Okay, in other words, c is a critical point. That's what that says, right? If f prime of c is equal to 0, it makes c a critical point. Then that critical point is a local maximum if the second derivative is negative there. And that critical point is a local minimum if the second derivative is positive there. So here's the picture that I have in mind when I think about second derivatives. This one right here, the first one on part 1, says if f double prime of c is negative. Negative means it's concave what? Down. So in my mind, I automatically think parabola looking like that. When I see negative derivative or negative second derivative, this is the image in my mind. And if the second derivative is positive, then I have this image in my mind of a parabola that's opening upward. What's happening right here at that orange dot? It's a maximum, right? That's exactly what this says is happening over here. And what happens at the second orange dot? That's a minimum, which is exactly what this is saying is happening. So there's a direct correlation between the second derivative and maxes and mins at critical points. You can't just do this and test it everywhere and say, oh my goodness, I have a second derivative that's positive, so therefore I have a... No, you have to have a critical point that you're testing it for this to work. So we're going to use this information then and find the critical points with the second derivative test to find out where we have local max and minimum values. And we're going to do this particular equation. We have a couple choices. We could divide each part by x, or we can use quotient rule. It doesn't matter to me which one you want to use. They're both probably about as much work. What would you guys like to do? Simplify and use the other rules, or use the quotient rule? Quotient rule. All right, everybody's in agreement even. Wow. Or at least if you aren't, you didn't say anything. So now you have to be in agreement. Okay, quotient rule. Somebody tell me what it is. Some of you like to move the numerator and denominator and switch things. So tell me what the numerator is going to look like here next. Okay, the denominator times the derivative of the numerator, 2x. Good, we got it in the right order. And then it's minus what? X squared plus 1 times 1, very exciting 1, over x squared. Fantastic. Let's simplify this mess. What do we get? Minus x squared still, actually, yeah. And then what? Minus the 1. Don't forget to distribute that negative over x squared. Then what? Okay. Well, that cleaned up awfully nicely, didn't it? Why did we find this derivative? We're supposed to be finding all critical numbers. Let's go back to those directions. We found a derivative because to find a critical number means to find the derivative and do what with it? Good job, Allison. Set it equal to 0. And technically, we want to set it equal to one of two things, equal to either to 0 or equal to does not exist. So if it's equal to 0 and I've got a rational function, what does that mean I'm doing? Where will this function equal 0? When the top is equal to 0. So this piece right here tells me I'm going to let the numerator, x squared minus 1, equal to 0. Where is this thing going to not exist? When the bottom is equal to 0. So I'm going to also need to find the location where the denominator is equal to 0. These are all locations where I actually would have second derivative potential issues going on. Now, in particular, on this one, I'm not going to need this because I'm not actually identifying, or let me say what, let me back up, let me say that differently. I know what's happening at x equals 0. What's happening at x equals 0? There's an asymptote, right? The original graph over x. there's an asymptote at x equals 0, so I know that even though that's a critical point, it's not a max or a min. Y'all with me? So this particular piece of information is not useful in what I'm working with. It's just the other piece that's going to be. So let's take a look at x squared minus 1, which looks like something I've already dealt with in the last problem, or last section of problems somewhere. What are my x values? Plus or minus 1. So I have two critical points, x equals 1 and x equals negative 1. And what am I supposed to be doing? What the directions say? Use the second derivative test. Well, what does the second derivative test say? It's right on your notes straight above this. It says something about the second derivative, right? So I'm going to need to find the second derivative next. Agreed? All right, so I need the second derivative. Do I have space over here? I don't. Okay, let me cut this. And then I'll move this over. All right, I need the second derivative, and this right here was the derivative. Agreed? We've already done the quotient rule once, so we should probably just do the quotient rule again. Agreed? All right, you guys are the ones who headed down this fun trail of quotient rules. So what do I do next? X squared, very good. And then times the derivative of the numerator, which is 2x, minus what? Right, so x squared minus 1 from the top and 2x from the bottom in either order. So numerator derivative of the denominator. All over the denominator, which was x squared, squared. We're going to clean this up a little bit because it does, in fact, clean up. This is 2x cubed minus 2x cubed. That was friendly. And I think we're going to have a plus 2x over x to the 4th. Does that look okay? What do you notice? Yeah, there's a subtraction in the numerator that simplifies. So I have 2x over x to the 4th. I could leave it that way for what I'm about to do. I could also reduce it by a power of x. So I could recognize that this is just going to be 2 over x cubed. But if you didn't recognize that, that's not the problem. The question wasn't find the second derivative and simplify it, right? The question is to use the second derivative to do something. What are we supposed to be using the second derivative to do? Local extrema. All right, so go back to this slide over here. It says the second derivative, when I find a critical point, and I have two of them, I have a critical point at 1 and a critical point at negative 1. But if I have a critical point, I can take the second derivative, and what do I do with the critical point? I plug those critical values in, and I look at whether or not I get a positive or a negative value from it. So over here, what I want to do is I want to find the second derivative at negative 1 and the second derivative at 1. So that means I'm going to take 2 over, and I'm going to plug in negative 1 and cube it. I'm going to do 2 over, and I'm going to plug in positive 1 and cube it. And what I really care about is what? The sign. Do I get a positive or do I get a negative? So what happens on the first one? The second derivative at negative 1. That one's negative because I've got 3 negatives on bottom. How about the second derivative at positive 1? That's a positive. Okay, so this is a second derivative that's negative. What is a second derivative that's negative? Tell me about the graph. It is concave down. A negative second derivative, the graph is concave down. So when the graph is concave down like this, do I have a maximum or minimum? I have a max, right? There's a maximum right up here in the curve of my hand. So this one tells me right here that this is a max. I should have done that a different color. And what happens when the second derivative is positive? The graph is concave up, and then I have a minimum. So this piece right here tells me that I have a minimum at x equal 1. Now, going back up to the directions, just one thing that highlight for you is this says critical numbers. It doesn't say critical points, so I don't need the XY ordered pair. I just need the X value. That's sufficient. So I need to write down my answer. I'll write it up here at the top that I have a local max at X equal what? -1. And I have a local min at X equal +1. That's the answer to the question that was actually proposed. Yes?
If we were to find points where it adds just for critical numbers, will we get a discount?
If you were to find the points when it didn't ask for the points, no, that'd be fine. You could definitely find the points, the ordered pair for that, and that'll be okay. Any questions on this one? Okay, we're going to do one more that's a little bit like the last section, where we're going to take a graph. It is a trig function graph, and we're going to identify significant features of the graph. We did this back in the last section. It was a rational function, and we found asymptotes and things like that because those were values that are sort of relative to that particular type of graph. We don't have asymptotes and sines and cosines, so we're not going to be looking for asymptotes on these. But we have some other features. So it says determine all significant features by hand and sketch a graph. So significant features could be asymptotes, but this is sine and cosine. They don't have asymptotes. So what are other significant features that it might be referencing? Critical points? What else? Well, critical points will turn into potentially maxes and mins, right? So this might include finding a max and a min. What are other features of a graph that are useful or helpful to determine? Because our goal is to determine these things and then just sketch a graph from it. Concavity is one. So we're going to look at concavity issues. There's one other thing that is usually one that we're going to look at. The slope. So in particular, I'm going to write it down a little bit differently, but it's related to slope. It's the graphs where it's increasing and decreasing. And the slope tells us that, right? So critical points. How do I find critical points? Just a reminder. First derivative equal to 0. And this the third thing I listed to, the increasing, decreasing, is where the first derivative is negative or positive, right? And then concavity is about the second derivative being negative, positive, or potentially 0. And when it's 0, it might be a point of inflection. Doesn't have to be, but using the concavity around it, we could determine whether it is or not. So these are the kinds of things that we're looking for significant features. And of course, if we had a rational function, we might also be looking for asymptotes. This one's not rational, though. Here's the good news. Derivatives are very easy to find with trig functions, right? Especially sines and cosines. You know those quite well. Once we get into secants and so cosecants and stuff, we have to start being more careful to remember them detailed. But sines and cosines are very nice. So what is the derivative of sine x plus cosine x? Good. Cosine x and then negative sine x. We're going to need to set this equal to 0 later and so forth, so I'm going to skip a little bit of space. But I want us to find the second derivative while we're at it. And we'll go back up to the first derivative and make some determinations in a minute. What is the second derivative going to be? So negative sine x minus cosine x now, right? It's actually just the exact same function we started with, but the signs are both switched because we found two derivatives of it. So that's actually a nice kind of feature too. Okay, let's go back up to that first derivative then and do what it is that we're setting out to do, which is to set it equal to 0 and to see what happens. Now, in particular, there's trig that we could do to do this. That is, we could move things to the other side, and we could do an inverse or an arc sine or an arc cosine and figure out what the angles are. I don't think that's probably our easiest approach. We are going to go ahead and move one of them to the other side, but then I am going to call upon you to try to think about what you remember about unit circles. or in particular about the graphs of sine and cosine, if that's a more helpful sort of approach. How in the world do we get the sine value, or where in the world do we get the sine value and the cosine value to be the same? Pi what? Pi over 4s, right? So like pi over 4 and 5 pi over 4 and 3 pi over 4 and 7 pi over 4, that's within 1 unit circle, right? So it's all of the pi over 4 type values. So that's useful information to us. So we don't need to do any anythings to find that, right? It's easier really to just think about where these trig functions have those same values. So this is pi over 4, 3 pi over 4, 5 pi over 4. I'm going to write the last one within, a full rotation, and then we'll pause.
Dr. Hans?
Mm-hmm.
Will 3 pi over 4, 7 pi over 4 apply? That's
Oh.
cosine and sine are either positive.
You're right. I wasn't thinking about that. So which ones do I need to exclude, Snyder?
3 pi over 4 and 7 pi over 4.
Okay, and say again why?
Because cosine can be positive and sine can be negative.
Yeah, the signs are actually opposite on those. Thank you so much for reminding me. There is a problem, maybe it's in your homework. Maybe. Where you're going to do one where there's sine squared is equal to cosine squared, and then the signs don't matter. But you're right, they definitely do matter here. Thank you for catching me on that. I appreciate it. Okay, so we do have just the values in quadrants 1 and 3, where the sine and cosine actually match in terms of their signs themselves, plus and minus. All right, fabulous. All right, so let's pause on this for a second, then come down here. Let's look for possible points of inflection now. So we're going to set the second derivative equal to 0. So what is it that we want on the second derivative then? What x values will this one be? The other one's the ones I just marked out, right? Yeah. Very good. So this is the 3 pi over 4 and the 7 pi over 4. And again, this is cyclic. It's going to keep happening, so etc. It continues. Let's do some graphing, okay? Our point was to sketch a graph by hand. So let me move this to the side so I have some space to do that. So we're going to have our graph over here. It doesn't matter how much of the graph, we're not being told specifically how much of the graph we want to show. So we can show from 0 to 2 pi. That seems quite reasonable. So we're going to go here from 0 over to 2 pi, and we'll fill in the details we know so far. We know that we have potential critical points at these pi over 4 values. So in terms of my graph, I probably need to have them present on my graph. So right now, this is halfway between is pi, and then I'm going to have to mark halfway in between these to get my pi over 4 values. Okay, let's think from a number line now. Let's go back up to the first derivative and think about what happens from a number line point of view. Hang on, let me see if I did it differently in my notes. Yeah, let's use that actually. Let's do this way. Instead of a number line, let's use the second derivative test. We're in the second derivative section anyway. It might be helpful to think of it from that perspective. It'll be certainly quicker since we already did the second derivative. What we'd like to know is we'd like to know what in the world is happening at these critical points, at pi over 4 and at 5 pi over 4. Do I in fact have maximum and minimum values here, right? That's what critical points are supposed to tell me. So when I graph these, am I going to actually have a peak or a valley here? And I can use the second derivative test to tell me that by finding the second derivative at each of those values. So the second derivative of pi over 4 and the second derivative of 3 pi over 4. I wrote it wrong, didn't I? Yes, thank you. 5 pi over 4 is what I meant. Thank you. There we go. All right, so let's take a look. Here's my second derivative right in, okay, sorry, I hit the wrong button. Right in here is my second derivative. What happens when I plug in pi over 4? First of all, let me just ask you, do I care about what value I get? Not really. What do I care about? The sign, is it positive or negative? So when I plug in pi over 4 into negative sine x minus cosine x, do I get a positive or a negative? I get a negative. Because sine of pi over 4 and cosine of pi over 4 are both positive, and then I've got negatives in front of both of them in this particular equation. If you weren't so sure, you can grab your calculator, and it will tell you the same thing as well with actual value to it. And you're going to get a negative value here. What happens when I plug in 5 pi over 4? Yeah, I get a positive. So there's this one. So if the second derivative of the graph is negative, what does that tell me about the graph? Second derivative negative. Concave down. If a graph is concave down, what's happening at that critical point? It's a max. So I'm going to have a max at pi over 4. And then the second one, of course, is the exact opposite. It's concave up. I'll end up with a min. Okay, so let's get those plotted. But in order to plot a point, an x value is not enough, right? No, it's not. I need an x value and a y value. So we need to take each of these x values, pi over 4 and 5 pi over 4, and I need to evaluate them in the original function that I was given. And I really would, in fact, like to have an actual real value and an approximation so I can graph it in a way that makes sense. So if I plug in pi over 4, what is the sign of pi over 4 in radicals? Do you remember? Square root of 2 over 2. What's the cosine of pi over 4 in radicals? They're both square root of 2 over 2. So what happens when I add square root of 2 over 2 to square root of 2 over 2? I get a square root of 2. So the exact value that I'm going to get over here is that this is pi over 4 square root 2. What is square root 2 approximately? I think it's 1.4. I think you're remembering pi over 2, which is about 1.57. So this is about 1.4. Can somebody double check that? Just square root 2? Yes, I got a nod. All right, so over here, if I'm labeling these, this is 1 and this is 2. At pi over 4, which is right here, I should be approximately at 1.4. So something about right here, like this. And that should be a max or min. That's my max. So I better be going downhill on either side of that particular point. So something like this. Make sense? The next location was at 5 pi over 4, which is right here. So what happens when I plug in 5 pi over 4 into this? I get the same thing but negatives. Yeah, I get negative square root 2 over 2, which is roughly negative 1.4. So something about right here. I need to connect my maximum to my minimum, which also needs to look something like that, right? So if I go backwards and I draw, not backwards, but if I go through here now and I draw this to connect them, they're going to connect something like this, right? What's the graph look like? It looks just like a sine or a cosine curve, doesn't it? With what exception? What's different about it? The what? The period's actually the same. It still happens between one full rotation of 2 pi. It's shifted a little bit off of either of their values. What else? But there is something that's different. The slope will be slightly different. Something else I was going for in terms of the picture, though. Like that we wouldn't have talked about in trig, I guess. Something we would have talked about in trig, I guess is what I mean. Do you guys remember the word amplitude? What's amplitude mean? It's not the x. That's phase shift. It's the y. How far up or down you go. This one has actually an amplitude of square root 2, right? It goes all the way up and down to square root 2 away from the x-axis. So it has this sort of a stretch involved, right? It's like it's been stretched up and down a little bit. Okay, do notice one other thing. Even in the way that we drew it, because of the necessity for how it was drawn, this particular location, and then over here right as well, which is my 3 pi over 4 and my 7 pi over 4, do those appear to be points of inflection? Do they appear to be places where on one side of it's concave one direction, on the other side it's concave differently? They do. So we've drawn it fairly well based on that information. Okay, I think we have one more example. Another one of these, sketch the graph with these characteristics. Sketch a graph of a function with the given properties. F of 0 equals 0, f of 1, negative 1 equals 1. F of 1 equals 1. F prime of x, we've got some details about that. And then we've got some details now about f double prime, right? So let's actually start at the beginning because it's the easiest information to actually match with our graph. What does the first pieces of information tell us? Points on our graph, right? X, Y ordered pairs. So let's start with those. We're going to have a point at the origin, it looks like, again. We've got one, f of negative 1 equals 1. So something like this. And f of positive 1 equals 1. So all of those have to match. Those have to be those exact details on here. Good so far? All right, let's take a look at what the the first derivative then is telling us. All of this pertains to the first derivative. It says the first derivative is positive. What does positive first derivative mean? Increasing. Somebody said it. That means my graph is increasing. So the graph is increasing when x is less than negative 1 and when it's between 0 and 1. So maybe a sign chart would help in terms of my increasing, my decreasing. Looks like the values they're giving me on my sign chart have to do with 0, negative 1, and 1, which makes sense because those are the x and y ordered pairs I just plotted. This one says that it's supposed to be increasing when we're less than negative 1. So it's increasing here. And it's increasing between 0 and 1, so it's increasing here. Organizing the information in some way that makes sense to you is going to really help in drawing the graph. And then the last piece of information that's underlined in orange says that the first derivative, you can't almost see it because I've highlighted over it, but the first derivative is negative when x is between negative 1 and 0 and then after 1. So what does a negative first derivative tell you? It's decreasing. So my graph needs to be increasing, decreasing, increasing, decreasing. So far on my graph, let me just sort of picture what we've got going on. All that we know so far is that it's doing something like this. Right? If this is all that I was given, I could stop in this graph that I just sort of threw in here that looks like my M. That would work. Agreed? Okay. Now let's go back and let's take a look at what's happening in terms of the concavity because that's new information for us. This one says the second derivative has these features. And I'm going to do another number line to try to give us some perspective. It actually doesn't tell us anything about x equals 0, so I don't really have that information to be worrying with. I just have negative 1 and 1. If you want to write 0 and you can, it doesn't hurt anything, but it's not going to do anything differently at 0 according to this information. So it says that f double prime of x is greater than 0. What does it mean for the second derivative to be greater than 0? Second derivative. Concavity, right? And it's concave what? Up. If the second derivative is greater than 0, it's positive, then it's concave up. So this one's telling me it's concave up when x is less than negative 1. So this is supposed to be concave up. It's also concave up between negative 1 and 1. And it's also concave up after 1. This graph is supposed to be concave up on these intervals, but not necessarily at negative 1 and 1. It doesn't tell us that, right? So my graph on the left-hand side of my first yellow or orange dot, right here, this piece, needs to be concave up, and it needs to be increasing from left to right. Can you sketch what you think that might look like? Yours may not look like mine, but draw something down for me. If you're using a pencil, it'd probably be great. If not, you might want to draw a second sketch if you didn't get it quite right before. Draw what you think it might look like for it to be increasing and concave up. Maybe you drew something that looked like this. Now, I drew mine like there's an asymptote along the y-axis, the x-axis. Did I have to draw it like that? No, I don't have to. It could go below the x-axis. That'd be fine. Is it okay if it doesn't? Yeah. Is it increasing from left to right? Is it concave up? Yeah, it is. If I drew tangent lines and I moved towards the right-hand side, the tangent lines would be increasing, which is the definition of concave up. Now I need to be concave up between the two orange dots, and it still has to connect to that bottom orange dot. So you probably don't have a lot of flexibility here. Your graph and mine are probably going to both look like this. Right? You got to connect the three dots. It's got to be opening upward. This is the basic idea in between. Now maybe on the right-hand side, you've got the mirror image of what you have on the left-hand side. We could certainly do that. It could look symmetric like this. Does it have to? No, nothing about this said that the graph is symmetric, so you could actually flat out make it look completely different on the other side. Well, not completely different. It still has to have the right characteristics, right? It's supposed to be decreasing right here, yeah? But after the number 1, it's supposed to be concave up and decreasing, which is why I know it's going downhill instead of, say, uphill, right? And I didn't actually make mention of it because I knew I had to have this concave up feature in between here. But notice, it is in fact decreasing from -1 to 0, and it is in fact increasing from 0 to 1, just like the sign chart said that it was supposed to. Any questions on that one? All right.